Alrighty, we got, let's get out of there. There it is. So we have 2.4 multiplication properties of exponents. Multiplication properties of exponents. Let's jump right in. We have like a series of examples here that maybe you'll pick up a pattern for, where if we're doing 2 to the first power times 2 to the first power, when you put all those together and then reset it and resimplify it, it ends up being 2 to the second. Just like here, okay, 2 to the second times 2 to the second, when you put it all together, so to speak, you end up with 2 to the fourth. And then let's keep this going. So write that out. Hopefully you don't have to pause the video too much if I go a little too fast, but as you write down. So, we have 2 to the third, which is 2 times 2 times 2, times 2 to the first, which is 2. But do you really need those parentheses there now? Or if you took those parentheses out, can I? Yeah. Like, what would you have? Wouldn't you just have 2 to the fourth, And then here, 2 to the fourth and 2 to the second, maybe separate. But when you put it all together, 2 to the sixth, and then 2 to the fifth, and then what would this end up being? When you have 2 to the third times another 2 to the third, but again, if you sort of thought of it as all those 2's together, 2 to the sixth. And that is a fire drill. Okay, hopefully that was a seamless pause and unpause for the fire drill. I think we're ready to move on, right? So hopefully you saw the pattern there. It's represented in this definition below, multiplying powers with the same base. So for every non-zero number a, and these are integers, like these powers have to be integers, and the base has to be something not 0. We're just going to, as you could tell back here, whenever we're multiplying like bases together, 2 to some power times 2 to some other power. And again, I should probably maybe throw this in here early on. It's usually x to some power, times x to some other power. This ended up looking like a 3. So if it was like x to the third power times x to the second power, it'd become x to the fifth power. But whether the base is a variable or whether the base is like a number like 2, if it's the same base with powers and you're multiplying together, you can, where does it say? Add? I was thinking maybe I could underline the word add, like emphasize the word add if it was written anywhere, like you're going to add the powers together. So here we go, just some very basic examples. 11 to the fourth power times 11 to the third power. See, again, like you could think about what's going on behind the scenes, because this would be like 11 times 11 times 11 times 11 times 11 times 11 times 11. You put them all together, how many factors of 11 do you have? 7 factors, which you could just shortcut to this answer because you know to add the powers. So this one, 5 is the base. Again, it's a little more legit. It's a little more required and important to know how to play with exponents when it's not a base of 5 or a base of 11. It's bases of like x or m or whatever, like some variable. But 5 to the negative 2 power times 5 to the 2 power, you can add those powers together and you're actually going to get the 0 power as in the final answer here. All right, feel free to pause the video and try these on your own real quick before unpausing, but here we go. Last chance to pause the video, because here we go. So 5 to the third times 5 to the sixth. You're going to add those powers together. That's the shortcut. That's how exponents behave when you're doing, because again, 5 times 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 5. Overall, it's 9 5s being multiplied together. This one ends up being 2 to the first power, because 4 plus a negative 3 results in 1. And then this one, yeah, if you were like, do I add all 3 of these powers together? Yep. Negative 3 plus 2 is negative 1 plus 5. So, yeah. And then apparently we're just doing like some other examples that get a little more complicated, I guess. So here we go. There's not much to say here. Look, when we're doing 2n to the fifth times 3n to the negative 2, keep in mind and remember that 2n to the fifth, right, that means 2 times n to the fifth. And over here, this 3n to the negative 2, this means 3 times n to the negative 2. So really, all of this is being multiplied together. The 2, the n to the fifth, the 3, and the n to the negative 2. And there's a certain property that we talked about last chapter that says you can like rearrange things and multiply in whatever order you want. So what's that going to mean for us? It means when we're multiplying these two monomials together, that's another way to describe it. Hey, we're multiplying a couple monomials together. The 2 can get multiplied to the 3 to be simplified. So what's 2 times 3? Well, 6. That goes back to second grade. And then we could also do n to the fifth times n to the negative 2. And to do that, okay, you do what with the powers? You add them. 5 plus negative 2 is positive 3. So this is the final answer to this example. Over here, see, once again, we have all of this stuff being multiplied. I know there's only multiplication symbols here and here, but technically it's there and it's there, and it's 3 times x to the 8th. What does that essentially mean? That just all of it's getting multiplied together. 5 times x times 2 times y to the 4th times 3 times x to the 8th. So you can do 5 times 2 times 3. Again, second grade, that ends up being 30. 5 times 2 is 10, times 3 is 30. Then it becomes a matter of, okay, I can do x times x to the 8th. Those can multiply together and simplify. So what do you get when you do x times x to the 8th? Keep in mind that the invisible power right here is 1. So wouldn't we add powers? Yeah. So we'd get 9, because it's like the 1 plus the 8. And then y to the 4th, is there any other bases of y to multiply by? No. So the y to the 4th, just nothing simplifies with it. And that's the final answer. You try. So again, feel free to pause the video to try these on your own before I just quickly reveal the answers. Last chance to pause. 3, 2, 1. Okay, so, at the risk of over-explaining it, 7 times what? I mean, technically you could think of it as, wasn't there technically an invisible 1 in front of that monomial, like of n squared? And technically, if you're thinking of these as like 3 separate monomials, the coefficient here is technically 1, and the coefficient there is technically 1. So if you want to think of it as 7 times 1 times 1, I mean, fine. Or you could think of it as there's nothing for the 7 to simplify with, to multiply with. So just 7. But then what are we doing with the n's? We have n to the second times n to the third times n, which again, remember, this technically has a power of 1. So what do you do to simplify n to this power times n to that power? Again, you add the powers. 2 plus 3 plus 1, 6. Okay? Similarly, 2 times 7 times 2, those simplify together. Spoiler alert. But the 2 times the 7 times the 2, that just ends up being what, 28? Yes, it does. But then, okay, x to the second, nothing simplifies with it. But then you could have y to the fourth times y to the third. Those add there. Here, same thing, like, wow, very similar actually. What the heck? The 7, and then m, any other m's? Yep. So remember, what's m squared times m? M to the third, because of the 1. And then n to the negative 2. Okay? Yeah, I thought that was it. So thank you for following along. Enjoy the rest of your day.